Okay, hello, welcome back. What exciting times we're having. We have an exam done. We are past the halfway point, but exam 1 was on chapters 1 through 5. Exam 2 is on chapters 6 through 10. So in some sense, we're halfway, but I assure you, some of these latter chapters, you can see for yourself. There aren't many problems assigned in some of them, and we will finish up with we have less than half the material to go. I would think that chapter 4 is maybe the most robust chapter. Chapter 4, chapter 5. A lot of stuff to learn and get familiar with forces. And with chapter 6 kind of under our belts, we are in pretty good shape, attacking the material and being in a good place moving forward. So, not sure which PowerPoint I want. Let me open up this one. Well, I'm not a big fan of this one. Hold on, just figuring out which way to present material that will be the most meaningful. And things are acting funny. So I hope you had a good weekend. Yesterday was a little much. My daughter teaches at a school on Martha's Vineyard, and the school year is wrapping up and she's getting ready to move out. And somewhere in the midst of that, went down and visited her. And so there's, just kind of pandemonium, because, it's a visit and it's nice and it's fun, but we're also loading as much stuff into our car as we possibly can to help her with the move out and made it through that excitement. Okay, so I think this is what I want to share with you. Work and energy. In the world of physics, in the world of biology, in the world of chemistry, in the world of geological sciences, there is a concept that is really pretty wild, that energy, which is a thing, can be transformed from one form to another. And so there's heat, which you can experience in the form of temperature. You touch something and it's hot, or you touch something and it's cold, and there's energy there. Heat energy in joules. There's potential energy. If I lift up a ball and then I go to drop it, but if I'm picking up a ball, if I'm holding it up above the ground, it has gravitational potential energy. And if I drop it, and it bounces all over the house. If I drop it, that potential energy turns into kinetic energy. Kinetic energy is the energy of motion. Anything that's moving and has mass, and everything has mass, anything that's moving and has mass has kinetic energy, also in joules. So heat, you're touching a hot stove or touching a cold ice cube, there's energy being transferred around. Getting hit by a ball that's thrown at you, there's energy involved. Dropping a ball, there's energy involved. It looks different, it feels different, but it's all this stuff, energy in joules. So brings us to the question, what is work then? Because work is going to, well, I tell a lot of the same stories over and over again. A career as an educator is a career where you're in a state of perpetual deja vu. Did I say this already? I think I said this already. Yeah, of course I said this already. And then, you just wonder if you said it to these people and if you're just repeating yourself over and over again. So I'm telling you a story that maybe I told you before, I don't know. There was one time I was teaching Physics 1, and I had a student in my class who was I think, sociology major at Salem State University. And every day after class, he would stay behind to talk to me because he was trying to figure out ways that physics and the laws of physics related to social movements, social constructs, social ideas. And so if we talked about kinetic energy, which is 1/2 mv squared, he'd be like, so mass, the M part of kinetic energy in terms of a social movement might be the people. How many people are involved or affected by a social movement? So there's the mass part. And then velocity, I forget what he came up with the analogy for velocity and velocity squared. And so he would talk about, try to consider the kinetic energy of like a social movement versus, what does that mean? There's another term, momentum, that we'll talk about. And, what does that mean in terms of momentum? It was just interesting. It was entertaining to try and, kind of consider how, you could, take physics analogies and apply them to other things. However, the language of physics is very specific. And so when we talk about work, it doesn't mean what we usually think it means, right? Like, boy, that was a lot of work. I moved, bags and bags of clothes and kitchen supplies from my daughter's apartment to my car. That took a lot of work. Or, you go to work and you work 40 hours a week or something, that, there's something there. But in physics land, and sometimes that's just helpful to think about that way, to take, your everyday definition of something and say, okay, right now, I'm not talking about everyday applications. I'm in physics land right now. In physics land, work is the application of a force over, and I don't mean divided by, I mean like through some distance. So your car breaks down, you pop it into neutral, and you get out and you push, and you're pushing your car down the road. You're applying a force in the positive x-axis. Your car is reluctantly rolling in the positive x-axis, and you are doing work. And what it will be, it's the application, the work is work done on an object by a constant force is defined as the product. So multiplying, that's what product means. multiplying the magnitude of the displacement times the component of the force that is parallel to that displacement. That sounds weirdly formal. In this case, if I'm pushing the car in the positive x-axis and it's moving in the positive x-axis, it's just force times distance, because the angle between the force and the displacement is 0 degrees, and you can try it on your calculator. Cosine of 0 degrees is 1. So if my force and my displacement are aligned in the same direction, and that's what parallel is, then it's full force. You know, all of my force is doing work on the car as it rolls down the street. So I could figure out how much work. I have to quantify how much force I'm pushing with. That's kind of hard to do. But if I knew how much force and I knew the distance, I know that I'm doing work. Now, what's weird here, if I pick up a bag off the floor, I've done work. Why? Because the bag has mass. It's a bag full of heavy pots and pans or something. The bag has mass, and there's a force. It's the acceleration due to gravity pulling it down into the center of the earth. But I am overcoming that force. So I'm applying a force equal and opposite to the weight of the bag, lifting it up. And as I do that, as I lifted a meter up off the floor, I've done work. Work equals force, the weight of the bag, times the distance that I lifted it up. Cosine theta, because the force and the displacement are in the same axis, they're both the positive y this time as I lift something up, then I've done work. What's weird is if I then walk across the room holding the bag, well, I'm applying a force on the positive y-axis, but my displacement is in the positive x-axis. Cosine of 90 degrees, cosine of 90 degrees is 0. I haven't done work when I carry a bag across the floor, but I only do work when I lift it up or when I put it down again, because I'm still applying a force as I let it go down in the negative y-axis, unless I just drop it, but that's a bad idea. So work equals force times displacement. Force equals mass times acceleration. So MA there, or MG. Acceleration is the change in velocity over time. Velocity is the change in displacement over time. So what are the units for work? If it Newton meters, kilograms times meters per second squared times meters, maybe it's kilograms times meters squared per second squared, whatever that is. It is all of those things and kind of none of those things, but it's all of those things with the unit joules. So all of this sounds crazy complex, but if you take it all in terms of something where we can conserve energy, and I'll talk about that, or not conserve energy, it becomes so much easier. I'm skipping the box guy for right now. For those of you who don't know, a toboggan is a sled. So there's somebody, gotta find my place. There's a sled, somebody sitting on it, somebody pulling it. Oh, are they pulling with their mouth? I don't know. Somebody pulling the sled. The angle of the rope is 25 degrees above the snow. They're pulling for a distance of 35 meters. And they're pulling with a force of 94 newtons. I guess I'll write in the 25 degrees. One of the picky things about physics is that you, the person, is applying a force to the rope. You're not applying a force directly to the sled. The rope isn't applying a force to the sled because the rope could just be sitting there flopped on the ground. But because you're pulling on the rope, you're exerting tension in the rope. The rope now has, if the rope doesn't break apart into multiple pieces, there is a tension force that is then exerted on the sled. So that's why it's saying this. There's tension in the rope of 94 newtons. It's coming from you, but we can't really say that. So how much work is done on the toboggan by the tension force? It's just as easy as you think it is at the end of the day. Work equals force times distance times cosine theta. So the work is the force, 94 newtons, times the distance, 35 meters, times the angle, cosine of 25 degrees. So the work done by the tension in the rope, 25 cosine times 94 times 35 is 2,982 joules. 2,982 joules. Is that a crazy number? Is that an expected number? It's good to develop some kind of intuition about what kind of numbers are crazy and what kind of numbers make general sense in the context of what's going on. If I said something weighed 2,982 kilograms or 2,982 newtons, like maybe you want to double check. If I said there's a kid sliding down a slide and you're trying to figure something out, and along the way you say, oh, this kid weighs 2,982 newtons, you should, maybe step back and say, oh, that might be a lot for a kid. Some number should set off an alarm bell in your head, because it's easy to make just a quick error on your calculator when you're plugging in numbers. If you miss the decimal point on 9.8 or something, so you're multiplying times 98. So in the context of work and energy, thousands, tens of thousands, hundreds of thousands are all reasonable values, depending what's going on. If you're pulling something for 35 meters, that's a long way to pull a sled. So 2,982 joules, 3,000 joules is perfectly reasonable. Now, we pulled at an angle, but person on the toboggan, what if you leaned way back and you pulled roughly parallel? I didn't do a good job with my parallel. Pulled parallel to the snow. So you're leaning all the way back. In that case, work equals FD cosine theta, but cosine theta is cosine of 0 degrees, which is 1. So in that case, it's just work equals force times distance. That would be 94 newtons times a distance of 35 meters. It's going to be bigger. 94 times 35, 3,290 joules. What does that mean? it would mean something in terms of the motion of the toboggan. If in the first case, you are exactly equal to the frictional force, able to overcome the work done by friction the whole time to move the sled at some sort of constant velocity, then it would move at constant velocity. In the second case, maybe your pulling force is greater than the frictional force. Therefore, you're doing more work in the positive x-axis than friction is doing in the negative x-axis. And in that case, the result would be acceleration, that the sled would be going faster and faster as you pulled by leaning all the way back and pulling parallel to the snow. And you probably wouldn't be able to keep up that for very long, but that's a possibility. Okay. Clear all drawings. Close that. Is work a vector quantity? Do tacos have dairy? It's not the greatest thing. If the ingredients of the thing include a vector, then the thing's going to be a vector. So can you do positive work and negative work? Well, yes, you can. I don't often work out, and when I do, I don't think I've ever really done free weights, but I am given to believe that if you are lifting up a barbell over your chest, neck area, and you lift it up into the air, it is an exceedingly bad idea to just let go and let it come crashing down on your neck. So you're applying a force in the positive y-axis as you lift it up in the positive y-axis. And then you keep applying a force in the positive y-axis as you let it come down in the negative y-axis. So in the first case, positive force, positive y-axis, times a positive y-axis distance. I've done positive work. And the second case, positive y-axis force, negative y-axis distance. I've done negative work. Your muscles don't care whether you're doing positive work or negative work. You'll get a good workout because you're applying a force through some distance. So you're not undoing the workout by letting it come back down. But this brings us to the work energy theorem. It's how work and energy are related, and we have to answer the question, what is energy then? There are two types of energy for right now. One of them is kinetic energy. I mentioned that one. Kinetic energy, 1/2 mv squared. It's the energy of motion. Anything that has mass, and pretty much everything does, anything that has mass and is moving at all has this thing called kinetic energy. And we quantify that 1/2 mv squared. Mass has to be in kilograms. Velocity has to be in meters per second for our units to work out as joules. And that's what we do. The other form of energy we're going to talk about right now, we've kind of hinted at. If you pick something up off the floor, then you have given it a certain quantity of gravitational potential energy. The source of that energy is gravity pulling down on it, mg, the weight force directed downward. And then if you lift something up, then you've given it a height, MGH. Anything that is above the floor, so maybe locally, in the room you're sitting in, anything that's sitting on the floor would have zero gravitational potential energy. But if you lift it up, now you've given it a certain amount of gravitational potential energy because it's up off the floor. And that's an easy thing to experiment with because you can lift something up and then drop it, and gravitational potential energy turns into kinetic energy as it falls down. Some of the big fun, if we were live in person in physics lab, would be having you go out to the staircase next to Meyer Hall 417 and walk or run up the stairs and figure things out about how much energy you're able to convert in a certain amount of time. That's called power. Power is work divided by time. Sometimes if you're buying an automobile, they'll talk about how many horsepower a car or a truck has. Horsepower, as you can probably imagine, is somehow related back to the average amount of power that a horse would have if you're pulling a cart or a plow or something. And we've kind of adopted that into our modern description of power. And we can convert power in watts, which is what we normally do, joules per second. We can convert power in watts to horsepower. For this example, when you climb the stairs, if we're not really concerned about you accelerating in the x-axis, and we can ignore that for now, each stair you go up is a certain height. So you're changing your gravitational potential energy, MGH. The M is your mass times gravity. And then the height is the total height that you climb as you go up the stairs. And then you can time yourself how long it took you to get to the top of the stairs and figure out your power. So work equals mgh, that height, your mg. Power is work divided by time. So it'd be mgh divided by the time it took you to get there. That's units of joules per second. Joules per second is watts. Watts of power. And not so very many years ago, I could talk about the brightness of a 25-watt light bulb versus a 60-watt light bulb versus a 100-watt light bulb. And what those would mean is, instead of gravitational potential energy, electrical energy being converted into heat and light every second. Truly, in a few short years, we have moved on from incandescent light bulbs that consume a lot of energy to LEDs that consume, far less energy and give off a certain amount of brightness. So we have moved on from describing the brightness of a light bulb in terms of the energy it consumes to describing the brightness of a light bulb in terms of the brightness of the light bulb. And so we talk in lumens now, which I don't really have a good instinct on yet, but maybe I'll develop that instinct as time goes on. But for now, they tend to tell you on the package that the light bulb, you know, whatever the quantity of lumens is comparable to a 60-watt light bulb for us old people that haven't evolved yet. All right, this is a concept test question. I guess it tells you a lot about me that the concept test questions that I tend to gravitate toward are the ones that have some math in them. In order for this to be a little more conceptual, they are rounding the acceleration due to gravity from 9.8 to 10. Just, it makes the math a lot easier. So we're at a bowling alley and the ball feeder mechanism has to exert some kind of force to push a bowling ball up a ramp. The ramp is 1 meter long. And then the ball is rolling along the top of the ramp to where you'll grab it to roll your next ball down the alley. I don't know how many people have been bowling since the pandemic began, but that's got to be a thing that's reopening now. So the question here is approximately how much force must be exerted sorry, on a 5 kilogram bowling ball to do this thing. So this concept is going to be pretty important. It's conservation of energy. At the bottom of the ramp, the ball has a certain amount of gravitational potential energy. At the top of the ramp, it has, a new amount of gravitational potential energy. Top, bottom. In order to give it more gravitational potential energy, we have to do work. So work equals the change in gravitational potential energy. Work is force times distance, so work equals force times distance. We don't need to worry about the angle because the force is directed parallel to the ramp, right? So the force and the distance, the 1 meter distance, are the same way. So force times distance equals mgh. So the force is going to equal mgh divided by distance. The distance is 1 meter. So m, 5 kilograms. We're doing that thing, 10 meters per second squared, rounding off the acceleration due to gravity to 10. The height is 0.5 meters divided by 1 meter, the distance. So 5 times 10 is 50, times 0.5 is 25 joules. So again, 25 joules is the energy. You divide by mass, or divide by distance, energy divided by distance, and we get the force in newtons. Sorry about that. And one of the problems with the way I wrote this out is that it looks like it's 1.200, 2.50. That's not what it meant. So answer number 1 is 200 newtons. Answer number 2 is 50 newtons. Answer number 3, 25. Answer number 4, 5, or impossible to determine. I tend not to do a lot of impossible to determine things. And the answer is 25 newtons of force. How do we get there? Well, we related the work that was done to the gravitational potential energy that the ball gained. Once we knew the gravitational potential energy that the ball gained, that was 5 times 10 times 0.5, so 25 joules of gravitational potential energy that was given to the ball over a distance of 1 meter. So the force must have been 25 newtons of force. 2 marbles, one twice as heavy as the other, are dropped to the ground from the roof of a building. Just before hitting the ground, the heavier marble has as much kinetic energy as the lighter one, twice as much kinetic energy as the lighter one, half as much, 4 times as much, or impossible to determine. I hope you know that if I take 2 marbles and drop them from the roof of a building, they will hit the ground at the same time. Gravity acts on everything with an acceleration of 9.8 meters per second squared, and it doesn't matter how heavy something is. It will matter for air resistance if something has a high surface area, but 2 marbles, probably indistinguishable in terms of surface area, and if I drop them from the same height, they will hit the ground at the same time, which means they will hit the ground with the same velocity. But even if you are aware that the 2 marbles are traveling at the same velocity, if you had to get hit on the head with one of them, something tells me that you would prefer to get hit on the head by the lighter one than by the heavier one. You know that there's some difference, and if it's not velocity, what is it? Well, it's kinetic energy. It's the energy that each marble has traveling at a certain velocity. And energy is 1/2 mv squared. So the V's are the same, but the M is twice as much for the heavier marble, which means that the heavier marble has twice as much kinetic energy as the lighter one. That is my son, Alexander. I had him in this class previously, and he is a high school junior now. Crazy. Oh, the water slide. Okay. Conservation of energy again. So we have a water slide. It's constructed so that swimmers starting from rest at the top of the slide, then you kind of scooch a little bit and start to slide down. They leave the slide traveling horizontally. So the slide kind of levels off at the bottom and you shoot off horizontally. That isn't dramatically different from water slides that I have seen out there in the real world. As the drawing shows, one person hits the water 5 meters away from the end of the slide, 0.5 seconds after they left the slide. If you ignore friction and air resistance, it's not a ton of friction on a water slide. Air resistance doesn't really have long to be acting on anything. Find the height in the drawing. This question is deceptively complex. Maybe not too deceptively. Maybe you're aware of how complex it is. So here's one bit of knowledge that we have. If the person leaves the slide and travels 5 meters in a time of 0.5 seconds, then their exit velocity is 5 meters divided by 0.5 seconds, 10 meters per second. All right, so what? Means they started at the top of the slide with gravitational potential energy, and at the bottom of the slide here, they had kinetic energy with a velocity of 10 meters per second. So we'll call this H1, and then there's another H. There's from the bottom of the slide down to the water. That's H2. That's where the question gets crazy complex, or at least clever. So at the top of the slide, mgh at the top, and 1/2 mv squared, that's a v at the bottom. As happens from time to time in the world of physics, mass appears on both sides of the equation, and so it cancels out. So at the top of the slide, it's 9.8 times h1, that's what we're going to call this height, equals 1/2 times 10 meters per second squared. 10 squared is 100, divided by 2 is 50. So 50 equals 9.8 h1. h1 equals 50 divided by 9.8. 50 divided by 9.8 is 5.1 meters. That's part of the height. The other part of the height, since this person was traveling horizontally, their initial y-axis velocity at the bottom of the slide was 0 meters per second. They're subject to the acceleration due to gravity, negative 9.8 meters per second squared. Took a time of 0.5 seconds for them to hit the water. You remember kinematics at all? We have 3 of our kinematic variables. We need to figure out one of the other ones. I don't know what their final velocity was when they hit the water, but I don't care. But I do want to know how far they fell to hit the water from the bottom of the slide to the water. So I look at my equations of kinematics. I want one that doesn't have final velocity in it. That would be x equals v naught t plus 1/2 at squared, which is y equals, since the initial velocity in the y-axis was 0, 1/2 times negative 9.8 meters per second squared times 0.5 seconds squared. This height from the bottom of the slide down to the water is 9.8 times 0.5 squared divided by 2. They fell another negative 1.225 meters down to the water. So it means that this is 1.225 meters above the water. So plus 1.225 meters is 6.325, 6.3, I don't know, 33 meters. It's the total height of the slide. This is a hard question, probably harder, just trickier, I guess, than I would ask you on a quiz or an exam. But the simpler part, to start at the top of the slide and go to the bottom of the slide, have gravitational potential energy get converted into kinetic energy, that would all be fair game. So just so you know. And then I gave myself space to do it out, but I decided to squish it in there. Some forces are constant and some forces are variable. One frequently encountered variable force is the force from a spring or a rubber band or a bungee cord, whatever thing you can kind of lay your hands on to experiment with maybe. But if you take a rubber band and stretch, it pulls back with a certain amount of force. But if you stretch further, it pulls back harder, further, even harder. Eventually it'll break or it'll slip through your fingers and snap on your hand and you'll say, ow. But a rubber band, a bungee cord, or a spring are all examples of variable force. And so the rules are a little bit different with a variable force. The work done by a spring as you stretch it or compress it is going to be 1/2 kx squared. What is K? K is a term we call the spring constant, and it tells you about how stiff or flexible a string or a rubber band or a bungee cord is. So this is all tied into this thing that we call Hooke's law, which doesn't involve hooks and isn't really a law, but we call it Hooke's law. Hooke's law is that force equals negative kx. The force of the spring is going to oppose the stretching, and so the force is negative kx, and it tells you how hard the spring tries to restore itself to its original position. If you compress the spring, it pushes back the other way. If you stretch the spring, it pulls back to try to get to its original position. So sometimes it's called the restorative force. But with the spring, the force is what you're pulling against. If you did a graph of force divided by distance or force versus distance, you would find the area under the curve is the 1/2 kx squared. That's the area of a triangle is 1/2 base times height. I don't know if you remember that from some geometry class sometime in your life, but because there's a slope of the line here, the harder you pull, the bigger the force. So it's a variable force. So we don't get a box, we get a triangle. If you're not pulling at all, there's no restorative force. If you're pulling really hard, there's a big restorative force, and you draw a line there. So the area under the curve is 1/2 kx squared, and that is the work that is done to stretch or compress a spring. And that takes us to the end of the Chapter 7 lecture. Hold on, let me stop sharing for a moment. Let me get our class page somewhere so I can see it again. Okay, so we've been kind of blazing through some stuff. Chapter 6, there's a couple of different videos you can watch on Chapter 6. So I'm hoping that you're feeling okay about navigating around our Canvas page. I figure if I have the whole course, I've done this in the past, I've had the whole course on one single Canvas page that just extends down and down forever. And you have to like scroll down super far to get to the current week. And I think I figured out that it's just a little bit of a pain. So each week of the class, week 1, week 2, week 3, 4, 5, 6, are all separate pages. So this one is our week 5 page. We have this week, Monday and Wednesday, and next week, Monday and Wednesday. So those are our last 2 weeks of the class. But if you want to go to last week, you click on the week 4 page and you go back to last week. And there's a key for quizzes. There is a video lecture for chapter 6 for you to watch there. I think this one was in the regular semester. Exam 1, maybe you've done it twice already. There's a video key for exam 1. If there's any questions from the exam that are bugging you, I'd recommend watching the video key. As always, I would suggest watching it at least 1.5 speed, if not double speed. So, you can slow down when it gets to the part that you have questions about, but I find it less annoying to watch me lecture if I speed myself up because I'm too slow. So there's that. There's also then on our current week page, another lecture video for chapter 6 that I think is from last summer. So, if you just want 2 perspectives on me going through the chapter 6 material, that's there. The chapter 6 homework, which is going to be the basis for the quiz on Wednesday, talks about things such as tension force, gravitational force, centripetal force, and then some information about things that are rotating around. Uniform circular motion was one thing, and then we're going to have some other stuff. So it's not a ton of questions, but if you haven't watched the chapter 6 videos yet, you're going to be very, very confused on this quiz. So I'm encouraging you to watch the lectures. We could talk about it now if you really wanted to, but it's something you can do on your own. And then when you do the homework, there's the videos of me talking you through doing these things. A radian is a way to measure an angle. It's kind of like degrees, but it's different. 57.3 degrees is 1 radian. It's just another way of measuring an angle. Do not put your calculators in radians, keep them in degrees. But we will be talking about radians as an angular measurement and then an angular velocity, how many radians per second something spins around. We will have time to do question and answer from the chapter 6 homework on Wednesday before the quiz, but you have that to work on. And then chapter 7, let's just take a quick peek at the chapter 7 homework because you don't want to delay doing that. Do I not have the chapter 7 homework videos page linked? What the heck, man? Insert link, course link, pages, chapter 7 homework videos. Save. So climbing the stairs, find the work to accomplish that. So work equals MGH, just that simple. This person pushing a box up an incline, the box is traveling along the incline. So that's the 4 meter part. So MGH for the box, but also, or no, actually force times distance for the box, because the force is parallel to the incline. But then the person is also changing his height. That's the MGH. You have a little creative work to do there. Elephant sprinter. The subway train that is brought to a stop by the spring. The work by the spring is 1/2 kx squared. We're solving for k. So some fun with math there. Yeah, I think you're okay for the chapter 7 homework as well. And again, the videos are there to help you along the way. Wednesday is a ton of fun. We'll talk a little bit about chapters 7, 8, and 9. No, 8, 9, and 10. I have a shortened version PowerPoint as we work through that material. And then I'll field any questions you have from chapter 6 homework as you prepare yourself to take the quiz on chapter 6 material. That is our last quiz. Then 1 week from Wednesday is our last exam on chapters 6 through 10. So on Wednesday, we will talk about all of chapters 6 through 10. Monday next week, our last week, on Monday, I will be going over things from chapters 7, 8, 9, and 10s, but really, 6, 7, 8, 9, and 10. And as you scroll down on that page, I have the practice exam for exam 2. I recommend trying to work through that as soon as Wednesday's over and you get over your exhaustion of taking another quiz. Take some time and look at the data sheet to get familiar with the terms there, and then see how many questions you're able to answer straight off the bat. And then if there are questions that don't make sense to you, be prepared on Monday to ask those questions. I'll go over anything that's bugging you that you're wondering about so that you can get through the home stretch of studying for exam number 2 and prepare yourself for 1 week from Wednesday. So that's all coming up. Right now, the thing on your plate, if you click on assignments, you can see all of the assignments for the course with their due dates, all of the homeworks and everything. When I go to student view myself, I am a very bad student. And so for almost all of my assignments, let me go to the home page. For almost all of my assignments, I haven't done them. So I haven't done any of my chapter 3 homework, and then I have more things coming. Anything that you haven't done, you can still do. So do make sure that you don't have any zeros for homeworks, because homeworks you can keep doing over and over again until you have a perfect score. Make sure that you do the quizzes and the labs Again, assignments, you can see all of the assignments for the course and their due dates. So try to tackle those. Also, if you're looking for anything, if you click on syllabus and scroll down, like you can see our schedule, obviously, but if you scroll all the way down forever, it just has this course summary. And so each date, what is due for that date. And so if you're missing anything, go ahead and get it done. Because there's nothing to be gained by having anything undone. You want to get all the points you can. I went into the system, and if you missed a problem from chapter 3 or skipped, some of the chapter 4 homework, I plugged in zeros, not to be mean, but to have it be noticeable to you. So if you didn't realize that you missed an assignment and you see a 0 there, there's, a red alert that you're missing that assignment. So try to get those done. First, chapter 6 homework, be good with that. And then start plugging away at the older material. Then chapter 7, because you should be able to do that now. And then we'll work on chapters 8, 9, and 10 later. Whew. Hey, that is enough for today. You have plenty of time right now to tackle some of this stuff. If you have questions for me, go ahead and either ask now or shoot me an email or set up an appointment on the appointment thing. If you want to work with the tutor ahead of the exam, go ahead and set up an appointment with Noelle. She'd be happy to work with you on anything. Otherwise, if you're feeling fine, keep plugging away. Gonna stop recording.